Hi folks, welcome back to AP Chemistry. This is Miss Gray, and today I am recording all by myself, so it's me and you. Here we go then. This is the podcast 2 for Electrochemistry, our last unit for the entire school year. So today we'll look at equilibrium and cell potential, how we can translate our E cell that we were calculating in our last podcast to an equilibrium value and a description of Gibbs free energy. Concentration cells are something new that we'll talk about, as well as electrolytic cells and the process of corrosion and electrolysis. So we've got a lot to do. We better get right to it. Okay, spontaneous redox reactions. In our last lesson, we learned about calculating cell potentials. Shannon helped me and did a marvelous job so that we could all understand how to use your reduction table so that we could get the cell potential for any pair of reactions, cathode minus anode. I'm sure y'all remember doing that. So, if we have a positive value for our cell, then that would be a spontaneous reaction when the value of E cell is positive. That's why we decided for a galvanic cell, we needed to pick the value that was the highest so we get the most spontaneous reaction. Likewise, when we have a non-spontaneous reaction, that simply means that the value of E cell is negative. Well, if we know what spontaneity means for the cell, then we can convert that into another measure of spontaneity for your reaction. That delta G value is also measuring spontaneity. So we know delta G is equal to minus N times the Faraday constant, which is like a cursive F, times the value of your E cell. And if this is a circle, then this is a circle, because that denotes standard conditions. 1 molar solutions at 25 degrees Celsius or 298 kelvins, and what else? Standard pressure. Okay. So N represents the number of moles of electrons. So we're going to be looking at our balanced redox reactions so we can know how many electrons are being transferred. We've got to keep track of that pretty carefully. And then F is a constant. It's called Faraday's constant, and it simply gives us the charge of a mole of electrons. So 1 electron has a charge of negative 1.60 times 10 to the negative 19 coulombs. And if we had a mole of electrons, then that means we're going to multiply this by Avogadro's number. And that's how we get that Faraday's constant, 96,500 coulombs per mole. And because of the relationship between charge and energy and work, these units ought to look very familiar to us too. We can translate this into joules per k-mole. How about that? We've seen those units before. And then finally, E naught represents the calculated cell reduction value that you got from taking the cathode minus the anode. Right? The more positive number, the bigger number, minus the smaller number. So we could have the most spontaneous cell reaction possible. Alright, well, here's an example. You know how we like to try it out ourselves, so let's give it a shot. So we're going to calculate the Gibbs free energy for the reaction of copper 2 with iron. So we start with half reactions. First of all, iron is going to ionize into iron 2. There's 2 oxidation states for iron. Make sure you pick the one that's the 2+. Copper is going to go, copper 2 is going to regular copper. So I have this written backwards from what's on our reaction. So we are going to flip the iron reaction because it's not written this way on our table. It's a reduction table, right? So we're flipping the iron, but we'll keep the copper as it is. Here's what your table says about it. Iron 2 plus 2 electrons makes elemental iron. And that value is negative 0.44 volts. For copper, we get the copper 2 plus 2 electrons makes atomic copper, and that's 0.34 volts. So this one, we want this direction. And we're going to do the same thing that we did before. Which value is more positive? The copper. So we take the cathode minus the anode, the highest value minus the lowest value. So if we have positive number, 0.34, and we're subtracting a negative number from there, then you're going to get something that's more positive than before. Right? How do we subtract a negative? We just turn this into addition. And you do not need your calculator for this. So add it up in your head, please. Overall, what do we get? Just have time to think it through. 0.708 volts. Good. Some of you are faster at math than I am, so I don't mean to sound patronizing if I ask whether you had time to think it through. You guys think way faster than I do. You're better at math than me. Yep, you heard me say that. You are better at math than I am. I've just learned a few tricks along the way. Alright, so we're going to put that value into our equation to solve for delta G, where N represents the number of electrons exchanged. That's here from our balanced equation, 2 electrons in this reaction. And then we have Faraday's constant and our E cell that we just calculated. Oh boy, I saved all this math for me to do. Wow, I don't know about that. I guess we better get a calculator out. So, get your calculator out, turn it on. I need you following along with me so that we know you can do this too. Oh, now what did I get? Back to the calculator. Here we go. Time to start pushing buttons, turn it on. And we're going to take a negative 2 times 96,500 times our E cell, which we got 0.78 volts. And my overall answer is a negative 150,540. And of course I don't get to keep all of those sig figs, only 2 sig figs are allowed. But I'm not going to round until I'm completely done answering this question. And yep, this is our final answer. So we'll just call this 1.5 times 10 to the, what is that, 5? Yep, 10 to the 5th joules per kmol. And then, of course, if we wrote this as kilojoules per mole, it would be 150 kilojoules per mole. Now, we've got this follow-up question. Don't you love this, how we have to always answer a follow-up question? So what is the KEQ for this reaction? Where delta G, we know, how do we get to K? This is something you did in the last unit when we were working on thermodynamics and kinetics. So let's add a blank slide and we'll do this calculation. I want to make sure that you can still handle a question like this. Alright, so KEQ is related to delta G by that Arrhenius equation. So we take our E raised to the power of minus delta G over RT, where R is the gas law constant and T is our temperature. And since we have this circle here, then we know what temperature we're at, right? That circle means standard conditions. So under standard conditions, when this reaction takes place, we're going to have E raised to the power of a negative, and then we had minus 150, and then some other numbers. Let's not round this just yet. I don't want to draw on the calculator. Let's get those numbers, 150,540. Alright, and then we're going to divide this term by R, 8.314 joules per kmol. Since I'm using joules here, I'm going to use joules down below. And then 298 kelvins. And this is all going to be part of e to the x. So I want to make sure that in our calculators we're doing this correctly too. So on your lawn, you're going to have to hit shift so we can get it the inverse of lawn, e to the x. We're going to have this be negative, and then I'm going to use parentheses for this. Negative 150,540 divided by the quantity 8.314. So back up 8.314, and we're multiplying that by the temperature, 298 kelvins. So I'll close out that quantity, but then I also need to close out my e to the x quantity. Hit enter, and we get the value for KEQ, which is, for 2 sig figs, 2.4 times 10 to the 26th power. Holy smokes, that's a big number. And if we have a large K value, then what that means is that our products are highly favored. We predicted this would be a spontaneous reaction, right? We have products over reactants in our K expression. So where we have a number that's this large, 10 to the 26th power, then this is ridiculously spontaneous. We're essentially going to convert all of this to products and have no reactants at all. Very, very spontaneous. Great. Well, I think we are cruising. It's sort of a calculation. You guys know how to work with KEQ and change that from delta G to KEQ. So let's look at another topic, the effect of concentration on your cell EMF. Remember, EMF is the electromotive force which is required to move electrons, and without electrons moving, we have no electricity. So we've got to be able to move electrons. And here's the tough question. Suppose that you're not in equilibrium. Can we use K if we're not in equilibrium? What happens? No, we sure can. So as the voltage is produced, then we're going to be consuming the reactants and producing the products, and that means your concentration isn't going to stay the same the whole entire time. But eventually, it's going to get an equilibrium, right? As the reaction proceeds, we get to a place where the reverse reaction and the forward reaction are occurring at the same rate, so there's no overall change anymore. And when we get to E equal to 0, our battery dies. And we're going to have to plug it in and recharge it, right? So we can get our reactants back. So if we have different concentrations than equilibrium concentrations, we have to use the Nernst equation. I think I said that wrong. It's not really equilibrium concentrations we need, it's the 1 molar. 1 molar is what gives us the E naught, the E with a circle thing on it. So if we have a concentration that's not 1 molar, we have to use the Nernst equation to adjust for some other concentration. And here's how that works. Any E, or potential, is going to be the same as your E naught, your standard cell potential under standard conditions. And then we're going to have to adjust this for the type of reaction that we have. So we're dividing by the number of electrons, number of moles of electrons, and Faraday's constant. And then here's where concentration comes in. Natural log of Q, the reaction quotient. We used K for equilibrium concentrations. And if we had K here, then E would be 0. But here we're looking at any concentration. So we'll use the reaction quotient. Not the same thing as K. But it's the same expression, right? We just put any old concentration values rather than equilibrium values. Well, look what happens here with these numbers. In the Nernst equation, if we're at 298 kelvins, then that means temperature is a constant value, 298. And R is a constant value, 8.314 joules per K-mole. And Faraday is a constant value, 96,500 coulombs per mole. So basically, we just combine all of these. And since we're switching to log base 10, it's not quite the same as natural log. This natural log, if we left that in here, we'd have some number of like 2.8 or something like that. But when we switch to the log base 10, then these constants all calculate out to be 0.0592 moles. And of course, we'll adjust this for the type of reaction we have, the number of electrons, and then the concentrations of our reactants and our products. And I know you're probably dying to see how this works, right? So let's give this kind of problem a try. Oh, wait, there's more. There's more about this because we said that E is going to be 0, but it's E naught that is 0 at equilibrium. If our concentrations are not both 1 molar, though, then we could still have some voltage, and we can predict what it will be by the Nernst equation. So we're going to use the Nernst equation not just for values at non-equilibrium values, but we can use it for EQ values, KEQ values as well. Cell EMF and equilibrium then are related when we know that E naught is 0 at equilibrium, and we apply the Nernst equation. Instead of using the reaction quotient, we're going to use K, the equilibrium constant. And this could come from a lot of different places, like pH. Remember, the Ka is equal to the pH of the half reaction. And so that was an important process for us to go through in your lab, so that you would know all the different ways we could get K to put into an equation like the Nernst equation. Now we're going to have to use it. And that's log base 10. So if I wanted to rearrange to solve for K, then I'm going to have to take this to the 10x to undo the log x, and then this whole blessed thing, right? 10 to the power of all this junk. Be careful how you put that in your calculator. You don't want to mess that up and have a mistake on your test because you didn't put the numbers correctly into your calculator. Now we get to work an example. And I purposely picked something that seems a bit complicated, just so you could have to think this through. So we have VO2 ions and zinc metal turning into zinc ions and VO2 plus ions. Be careful not to mix up the VO2 plus ions with the VO2 with a plus 1 ion. So the vanadium dioxide concentration was a 2 molar, and the VO concentration, vanadium monoxide, would be the 1.1 times 10 to the something molar. I'm not sure what I meant to have there. That's kind of scary. We'll keep going. We'll find out if I have made a mistake. And then the hydrogen ions, where would those guys come from? Probably from the water, 0.5 molar, and zinc is also in solution at 0.1 molar. So let's write our reaction. Can't solve a galvanic cell problem if we don't have reactions. So the redox reactions always start with a half reaction. I want to go back. I want us to find this on your table, because you may see something like this and say, I don't even know where to start. I don't know what to do. Well, of course you know what to do, because we don't have enough oxygens. So what do? We've got to add water to balance the oxygens. Vanadium is balanced. Oxygens were not. So now if I have 2 hydrogens on this side, I'm going to need to have 2 hydrogens on the other side. So we add those protons here. And then we'll have to figure out how many electrons are going to be transferred in this reaction. Oxygen is a 2 minus, and there's 2 of them, so that's a -4 for oxygen. And then we have a positive overall charge, +1. Let's figure out what vanadium's charge should be, the oxidation state here. Got it? We're going to move the -4 to the other side. It becomes a +4. So vanadium's a 5 here. What is vanadium on the other side? We have 1 oxygen and an overall 2+ charge. So one oxygen is a -2, and vanadium is our X that we're trying to figure out. So we're going to move the -2 over, and it becomes +2. We add it to the 2 that's already there. This vanadium is a +1. So how many electrons were transferred, and on what side shall I put them? Looks like we're losing electrons here. Nope, I lied, gaining electrons. To go from a +5 to a +4 is the gain of electrons. And we only need 1 for those dead ones. So I put 1 electron on this side, plus 2 protons, plus our ion, gives us the vanadium oxide with a 2+ charge, and water. Alright, let's find that reaction on your table, and I'll show you how we just did a whole lot of extra work. We did it for a reason. I needed you to practice, but it's already printed here on your reduction table. You don't have to do half reactions anymore. This is one you'll have to look up in Appendix E in your book, just to check, double check the values that I'm using and make sure that they're correct. But here's what I've got. Let's see. We balanced it the same way, but notice, since the zinc is gaining 2 electrons, then I've got to have my vanadium part multiplied by 2. We're going to multiply the electrons by 2. That's important. We're not going to multiply the voltage by 2. Don't multiply your reductions by the stoichiometry values. So then when we add the 2 together, this is really critical that you do this right. Get your 2 half reactions and add them up to make a whole reaction. And we flipped this, so we're going to take our cathode minus our anode, and when we minus a negative, then of course we get a positive value, 1.76 volts for the overall reaction. And when we do the equilibrium expression, the stoichiometry becomes super important. So we're not at equilibrium values, we're just going to call this Q. It's products over reactants. So the zinc is raised to the power of 1, and it's zinc with a 2+ charge. If you don't put the charges in, it's wrong. And then VO with the 2+ charge is raised to the 2nd power because of our stoichiometry here. So products, shall we include the water, liquid water? We rarely talk about the concentration of water in water, so let's leave that out of our equilibrium expression. We already knew that. Now we have hydrogen ions in solution, and by stoichiometry we know we're going to be raising that to the power of 4. And then the VO2 plus 1 is raised to the power of 2. And then zinc is a solid, so it's not going to be featured in our equilibrium expression either. So now we've got our equilibrium expression, and we have values to put in there. So in the place of the zinc, we're going to put in the concentration of the zinc that we started with. So this is 0.1 molar. And then VO2 plus, here we go, yeah. Well, I'm going to put 1 molar, but remember we had a question. Oh, no more question. It's 1 times 10 to the minus 2. Gosh, I wonder if I did that right when I solved this problem, because I didn't have that subscript there, superscript there before. And then VO2 was 2 molar, and that's raised to the 2nd power. Whoops, I need to raise that to the 2nd power. And then hydrogen ions is 0.5 molar, and that's raised to the 4th. So, put those values into your equilibrium expression, and let's solve. Check and make sure that that's the right answer, since I was worried about that superscript. I'm a little bit concerned, but I've checked this twice. You know, like Santa Claus, checking it twice. And so you guys check it. If I have a mistake, please let me know so we can fix it for next year. Great, well let's put this into the Nernst equation. Here's the Nernst equation again. This bad boy. We're at 298 kelvins. So our E is going to be your standard potential, which we just calculated, cathode minus anode. And then Q we just calculated, 4.5 times 10 to the minus 5. Gotta get my pen to keep up with me here. 10 to the minus 5. And so we put that into our equilibrium expression. Don't forget, we're using log base 10, not natural log. So let's get the calculator. So I want you to see how we would put this in. And here's what I would do. You're welcome to do it in whatever order makes sense to you, but I want to work this through step by step. What I would do first is do the log of 4.5 times 10 to the minus 5. So I'm going to figure out what that is first. There's that number. And so this quantity I know is negative 4.3467 and all that other decimal places that we don't really need. Now what do we do with it? We're going to multiply by a negative 0.0592, and I probably should have parentheses here. So I'm going to insert parentheses. That way I know I'm getting it to do what I want. We're going to divide this by 2. Well, only one division sign. And then close the parentheses. Then we'll multiply. I don't want to do the wrong order of operations here. Alright, so then I have a 1.128664. And here's our Nernst equation. I was trying to move it to see here, but we'll just look over here. I have this quantity all solved now. I'm going to combine it with my 1.76 volts from before. So let's add 1.76 volts. Since these are positive numbers, that's how we combine positive numbers, is addition, right? That's the operation we need. And I get 1.88866494. We better only keep 366. So 1.89 volts is the new potential when we're not at 1 molar concentration for all of our reactants. In other words, the voltage increased when we changed from 1 molar concentrations for everything. Compare this to what we have in our Q from before. Oops, this is times 10 to the minus 2. And see if you can explain, using Le Chatelier's principle, why did the voltage increase for this reaction? I'm not going to do it for you. You get to think it through on your own.